Here we have a rational function. A rational function is some expression in x, or just a number. It's just a number in this case, 1, divided by another expression in x. Usually that expression in x is linear. Linear means we just have x to the power 1 in it. We don't have x squared. Actually, the rational functions that you'll be dealing with are have linear expressions. It's called a rational function because a rational number has the form a over b. Rational comes from the word ratio. A is to b, or a over b, where a and b are both integers. So that's just a bit on the form of this function. Now, x is a real number and x is not equal to minus 2. Why is x not equal to minus 2? Well, if we try to calculate f of minus 2, what happens? We just replace x with minus 2. So we have 1 divided by minus 2 plus 2 is 1, so we have 1 divided by 0. Now what's 1 divided by 0? Well, if you try to do that on your calculator, you'll get an error. The problem is, whatever it is, suppose it's equal to a. If we multiply a by 0, we get 0. A multiplied by 0 is 0, no matter what number a we have here. If we multiply it by 0, we get 0. We don't get 1. If we cross multiply, we should get the number on top. So there's no such number, a. If we take the number 1 and divide it by a very, very small number that's close to 0, suppose we divide it by 0.0001. Well, that's just 1. What have we got here? 5 zeros. So we get a very large positive number. And if I make this number even smaller, suppose I add in another decimal place. So we have 6 decimal places. We get 1 million. So you see what's happening as we get a number, as the denominator gets closer and closer to 0, this number blows up, becomes very, very large. We could either get a very large positive number or a very large negative number. We get a very large negative number if we're approaching 0 from the left. Suppose that we had 1 over minus 0.000001, then our answer would be minus 1 million. Okay, you go to your calculator, take 1 and divide by this number, you'll get minus 1 million. So we could either have a very large positive or a very large negative number. So we say that 1 divided by 0, depending on how we're approaching 0, is an infinitely large positive number or an infinitely large negative number. So if we're looking at the graph at minus 2, our function is not defined. So there's a break or a discontinuity in the graph at x equals minus 2. So here's the x-axis. This is minus 2 on the x-axis. So we just put a vertical dotted line indicating that break or discontinuity. This vertical dotted line is called an asymptote. This is the vertical asymptote. Asymptote. The equation of this asymptote is x equals minus 2. A vertical line has an equation of the form x equals constant. The constant in this case is minus 2. That's the value that this line passes through on the x-axis. All the points on this line have the property that their x values are minus 2. For example, this point here is minus 2, 2. This point here is minus 2, minus 1. This point down here is minus 2, minus 3. This is minus 2, minus 2.5, and so on. So this equation is all we need. Y does not appear in this equation. It's a very simple form for a vertical line. It's just x equals a number. So the function is not defined at minus 2. So that's why this is stated in the question. X is not equal to minus 2. But the function is defined for all other real numbers. X. We want to copy and complete this table. So you can see in this table that f of x has been evaluated for certain values of x. F of minus 4 is minus 0.5, for example. Okay, if you take minus 4, plug it in here for x, and evaluate this, you will get minus a half or minus 0.5. F of minus 3 equals minus 1, that's shown. So we have to calculate f of minus 5. So we just copy out this function, replace x with minus 5, and evaluate this thing. So that's 1 divided by minus 5 plus 2 is minus 3, plus 1 divided by minus 3 is minus 1/3. The next x value we must evaluate f at is x equals minus 1.5. So we just copy this out, replace x with minus 1.5. So we have 1 over minus 1.5 plus 2. Minus 1.5 plus 2 is plus 0.5. We have 1 divided by 0.5, or 1 divided by a half. That's the same as 1 multiplied by 2 over 1, which is 2. F of minus 1 is 1 over minus 1 plus 2, or 1 over 1, which is 1. F of 0 is 1 over 0 plus 2, which is a half. F of 1 is 1 over 1 plus 2, or 1 over 3. The diagram shows part of the graph of the function f. Copy and complete the graph from x equals minus 5 to x equals 1. So some of these points have been plotted. For example, f of minus 5 is minus 1/3. So if we go to minus 5 on the x-axis, then we go down to minus 1/3. So we go down, vertically down a distance of 1/3. So you can see if we project across here, this is minus 1/3 on the y-axis. So that's this point here. F of minus 4 is minus 0.5. Project across here, this point here is minus 0.5. F of minus 3 is minus 1. So f of minus 3 takes us to minus 1. F of minus 2.5, minus 2.5 is here. And if we project down, we get to minus 2. This point is coordinates minus 2.5 minus 2. F of minus 1.5 equals 2. So minus 1.5 is about here. And we get 2. So that's this point here. F of minus 1 equals 1. That's this point here. F of 0 is a half. It's about here. F of 1 is 1/3. That's about here. So these are points on the graph. We get a smooth curve when we join these points up. Okay, so if we could imagine calculating the values of f at more values of x, we'd have a smooth curve here. By the way, for rational functions, functions of this form here, we will have a discontinuity or break at a value of x that makes the denominator 0, minus 2 in this case. So we'll see two sections to the graph, and both sections have the same shape. As a matter of fact, we can get the image of one section from the other section by projecting through this point here. Projecting points, say, in this section through this point. For example, if I take this point here, which is coordinates minus 3, minus 1, and project it through this point here, which is coordinates minus 2, 0, we'll end up with this point here, which is coordinates minus 1, 1. So get the image of the point minus 3, minus 1 under central symmetry, and the point minus 2, 0 will give us a point with coordinates minus 1, 1. And we can do that for all the points on this section. Now another thing you should know is that for values of x close to minus 2, the value of the function blows up to either plus infinity or minus infinity, as I explained to you earlier. Suppose I take a value of x just to the left of minus 2. So a value that's very close to minus 2. Say the value minus 2.001. This value of x is less than minus 2. It's to the left of minus 2. Suppose we work out the value of the function at this point. Well, that's going to give us 1 over minus 2.001 plus 2 is minus 0.001. And if you work this out in your calculator, what you will get is minus 1000. So you see you get a large negative value. So when x is minus 2.001, that's this point here, the value we project down vertically, because we want to go down to minus 1000. So we get a large negative value. Now, if I was to make this value of x even closer to minus 2, say I made this minus 2.0001, stuck in an extra 0 here, I get minus 10,000. So you can see what's happening as x approaches 2, our function f of x, or 1 over x plus 2, is heading towards minus infinity. If we approach 2 from the left, that's what this minus sign, we approach 2 from the left, or we can write it like this: limit as x tends towards 2 from the left of f of x is just this here, is minus infinity. Similarly, you can imagine approaching minus 2 from the right. Say take a number that's very close to minus 2 but greater than minus 2. This number here, minus 1.999. Okay, remember we have a number between minus 1 and minus 2 here. This number is very close to minus 2. It might look like this, minus 1.999. If we evaluate f of that, we get the following. This is 1 divided by 0.001. We get plus 1000. So for this value of x, we'd be going up to plus 1000. So I can extend this graph to show it approaching the vertical asymptote at x equals minus 2. Just put an arrow on it to show that the graph approaches the vertical line x equals minus 2 but never crosses that line. I could even take a value closer to minus 2. If I were to calculate this thing, I'd end up getting plus 10,000. An even larger positive number. So you can see what's happening as x approaches 2 from the right. Plus sign indicates we're approaching 2 from the right. F of x tends towards plus infinity. Our more concise way to write that is limit as x tends towards 2 of f of x is plus infinity. Another thing you should know is that if we take x to be a very large number, it could be a very large positive or a very large negative number, when we work out 1 over x plus 2, when we get f of that number, we will get very close to 0. So what happens is the graph approaches the x-axis from both sections, but never crosses the x-axis. So we have this, the x-axis is actually a break or a discontinuity in the function. So the x-axis is actually a horizontal asymptote. For example, suppose I take a very large positive number. Suppose I take f of 1000. That's going to be 1 over 1000 plus 2, or 1002, which is a very small positive number. It's approximately 0.001. And if I increase this number, if I add on another 0, so I get f of 10,000, then we would have 10,002, which is approximately 0.0001. But it's still positive. So this section of the graph will be above the x-axis because it's always positive for very large values of x. But that positive number is getting smaller and smaller. It's getting closer and closer to 0. So the y values of points on this tail of the function are getting smaller and smaller, getting closer to 0, but never reach 0. That's why we put this arrow. And similarly over here, if we take a very large negative number of x, if I change negative value of x, if I change this to minus 10,000, then we'll have what we get here is 1 over minus 10,000 plus 2. Now minus 10,000 plus 2 is minus 9,998, but that's almost very near minus 10,000, so it's approximately 1 over minus 10,000, or minus 0.001. So we get a very small negative number. So you can see what happens as the values of x increase in the negative sense, our function is approaching 0. But from below. So the y values of points on this tail of the curve are negative, but they're getting closer and closer to 0 as x goes off towards minus infinity. So we just put an arrow on this section of the curve.